So let's begin. This is the third and the last presentation about the debugger. This is the most kind of smart and useful features of the IntelliJ Debugger, which we have so far. I call it professional, but it doesn't mean that these features are hard to use or somewhat for professionals only. No, not really. But for some reasons, they are not that widely used, which we are trying to solve at the moment. But let's start with some things which I forgot to tell you about on the previous talk. And number one is the color filter, which is a special filter right here in the breakpoint. So the example we had from last time, we had some work being done in the warm-up section and in the real work section, and we were interested in the real work. So we set a breakpoint in the work method, and we can see that it is triggered from the warm-up. So last time I showed you how to filter this using the dependent breakpoints. So you set a breakpoint somewhere here, and you set this breakpoint as a dependent from that breakpoint. So with the color filter, there's an easier way to do this. So if you see the breakpoint and you have some easy way to specify the color for it, you can call the intentions menu and say that you don't want to stop if it is called from the warm-up, or stop only if it is called from the warm-up. And in this case, we don't want to stop it when it is called from the warm-up, because the warm-up is the color frame. And we say it, we continue, and now you can see that we stop only in the real kind of part of the application which we are mostly interested in. Also, if you go to the breakpoint settings from here, you can see that you can specify not only the exact method with the signature and so on, but also you can specify the wildcard. So for example, like any method warm up with any signature will be used as a filter in this case. Or you can say that you want like any method from this class, and if you use a filter like this, we will for sure not stop anymore, because, well, real work is a method from this class as well. But I think you get the point. Another thing is that renders can be created not only for the objects, but also for the primitive types and arrays. Let me show you. So here we have the integer value, and for integer value we have some built-in renderers like hex presentation or a binary presentation, and you can quickly switch them. But what if, for example, you want them both at the same time for any integer value? This is possible using the custom renderers. So you can create it for a primitive type, and you specify something like this. So you want it to start with the hex string, and you reference the value as this, even though it is not an object, but anyway, we can do that in the debugger. And then you create the binary representation as well. So this way, it will create a renderer, and every integer in any place in the program will be presented using this renderer. So for example, here, and if we go inside the printline method, you will see that any number integer value will be presented like this. Let's find it somewhere here. Okay, here. So anywhere. And also it is possible to do that for arrays. So for example, let's pass some parameters here to the application. And restart it. And you can see that the args array is presented in this nice and convenient way. And that is because I already created the renderer for this, which is implemented this simple and easy way, because we have a special method for this in the arrays class. Also, I forgot to tell you that we have special built-in renderers for images. And if you do some like swing programming or something like that, you can quickly see the content of the image right in the debugger. Oops, I forgot to remove the breakpoint. So here you can see the image icon, which contains an icon, and it is loaded from the image on the disk. And we can click on this show icon link and see the image. And this is a really nice viewer in the editor itself. So you can quickly see what's inside the image objects in the debugger. But more than that, if you set a breakpoint inside the paint method of the components, so in our case, let me show you. This application shows a big button, and this button contains the simple text. It is small and here, and a huge icon, which is a JetBrains logo. So we can put a breakpoint inside the paint component for this, and step-by-step debug how the component is painted. So this one is a J panel we are not really interested in, and this one is a J button, which is what we want to debug actually. And you can see that the image icon here is what we have, and you can also see the real image from here. So let's step-by-step see what's happening inside. And we step into and step over until we see that something interesting is happening here. So let's skip this until we paint the border. So right now in the graphics object, there's also the show image link. And if you click there, you will see that the graphics buffer is empty right now because nothing has been yet painted to that. After we paint a border, so we can step over here, we can show the image again and see that now we have, if you can see that, we have the border, like this rounded squares painted here. And then we can skip to the icon painting. So this line here paints the icon, so we can step over, show image again, and we can see that now we have not only the border, but also the icon. And there's some space here left for the text, so we can skip to the text painting somewhere here. And you can see that now we have the button fully painted. So this way you can debug how the components are painted on the user screen. Let's get back to the demo. Oops. Another nice thing is the lambdas. So in streams in Java and in some other places, users can write several lambdas on one line, and it was really hard to debug such things because debugger knows about a line, and if there's a lot of things happening on one line, it's really tricky for that to be debugged. Well, not in IDEA, because we have some special things for this. So if you try to set a breakpoint on a line with several lambdas, you will be asked about where exactly you want to stop. So every lambda is highlighted in this situation. And also, you can set a breakpoint on the line itself, and it will stop only once. When you first enter the line, you can set a breakpoint on every lambda. And also all is really the, like any location on the line. So every lambda on the line and also the line itself. So let's see how it works. This one is a line breakpoint. So we only stop here when we start the application once. And if we kind of continue, we will exit the application for sure. And if we stop somewhere inside the lambda, we will really stop on this line, but only when we proceed up to the stream processing. So you can see that we enter here with the I equals 2, and if we resume it, also 4 and 6 and so on. Also, if you really interested in any location on the line, this is also possible. Now you can resume and you will stop in every lambda or anything else on this line. Also, if you haven't set the breakpoint in advance, but you appeared on such line and you do the step into, debugger will ask you where exactly you want to step into. And you can see that it's not only about method calls here, like off a filter, and of course you will enter these exact methods, but also there are several lambda expressions here. So you can click on this lambda and you will stop when this lambda will be executed on this line. So this is really useful and easy way to debug streams. And another funny thing about deleted breakpoints. So if you have a breakpoint fully set up with a condition, with the, some filters, with the evaluate and log field, and then you accidentally click on that and delete it. So what do you do? Well, actually, there are two ways to fix this. And one of them is there's a special action called restore breakpoint. And what it does is basically restore the last deleted breakpoint. So voila, we have it back. Another way to do that, so I deleted it again. Well, not accidentally, but anyway. Another way to restore the breakpoint is to set a breakpoint back. And of course, it doesn't have any setup, but it has this nice link, like restore previous breakpoint, because it knows that you have just deleted a breakpoint on this line. So you can click here and you can restore your breakpoint. And later in the presentation, I will show you another way how to handle this, which is more proficient. Okay. So now let's start with the real nice professional features. And the first one of them is the mark object. So if in the program you are interested in a specific object, so for example, here we have a string object, and for some reason we want to remember this exact object. And if we see it in any other context, we want to make sure that this is the exact object we had before. So you can mark it. This is called the mark object, and you can specify the, I don't know, the label for this, and also you can specify the color for this. If you have several of them, you can distinguish them by the color. So I don't know which one. I like orange. Okay, so now the object is marked with this label. And if we proceed inside the println method, you will see that any occurrence of this object will be highlighted with this nice label. So if we go inside the, for example, value of, and then inside the toString, you will see that not only this is marked with this label, but also the frame itself, because, well, toString is called for the marked object. So this is really kind of useful to be able to detect the objects you are interested in. But there is one more kind of really useful feature of the labeled object. And this is that labeled objects could be accessed from anywhere, actually. So for example, if you have appeared in another thread, from where you, of course, you cannot access that object anyhow. It's another thread. It doesn't have anything kind of even close to that context here. But we have marked the object already. So in any context where we can evaluate an expression, we can type the name of the label, then underscore the debug label, and the completion will help you here. And this expression will evaluate to the object which we have marked before. So in any context where you can evaluate, so you can create a watch from this, and this watch will be available in any frame, anywhere, in any thread. You can create a condition for a breakpoint, checking, for example, that this object is the same as that object that we have marked already. This is also possible. You can create a call a method for this, or you can kind of make an expression from that. So for example, you can call a method from, I don't know, from current context using the object that you have labeled before. This is really useful sometimes as you can access it from some places where before that you were not able to see the object anyhow. So this is about the mark objects. Now, now you saw that we have some things we can use to see what's happening in the program, even if we don't have the exact objects in the context where we are right now. But the debugger is actually provides you much more. So don't think that when you debug an application, you are kind of only in the place where you are right now. Like you have a thread, you have a stack, you have a frame. So you can access only what's there in the frame, or like local variables or referenced variables from there. It's not true. So debugger knows everything about your program. And to provide you with this information, we have a memory view. So memory view, think about it as a snapshot of your memory, but it's not a snapshot, it's a real kind of access to the memory of the application. So you have a list of all classes and all objects in the Java heap of the application that is being debugged. So for example, we have 4,000 plus strings in the application right now, even though we don't have any of them in the current context. So we can double click there and see all the objects here. And also we have a filter here. So you can specify a condition written in a regular language, well, in programming language, in Java in this case. And you can filter that. So for example, we are interested in strings with the length more than 100. So it will apply this expression to every string object in the Java heap and provide you with the strings which are longer than 100 symbols. So what about 1,000 symbols? Yeah, there are some. So what can you do with this information? Because now you know that there is a nice string IDEA and so on. So from here, you can show the referring objects. So really what objects reference this particular object. So this is almost the same as you can do in the memory profiler or when you open a memory snapshot in any memory analysis tool. So you can see that it's a locale object from Java, which for some reason reference this super huge line. What else from here? So for example, you want to find a string which starts with a special prefix. Actually, any expression which you can apply in the application, you can apply in the filter in the memory view. This way, you can find any object in the heap, and also then you can mark it and provide it with a nice name. I don't know, string 1. And then, as I have shown you before, you can reference it from any context. So for example, if you have several objects of the type you are interested in, so let's continue to the next breakpoint. So now we have 3 objects of memory type, like memory is a class. So of course we have them here in the context right now, but it doesn't mean that this is always be like this. So for example, if we step into the print line method now, we don't have any of them here, but we can quickly filter this in the memory view, and now we have all of them here. So if you know that you have some interesting objects in the heap, you can quickly find them from the memory view, reference them, or use them from your current context, or you can change them. So once again, it is, of course, possible to do any modifications to that objects in the memory, the same way you do that with the objects in the current context. Also, in the memory view, there are some nice features like the diff column. So when you do steps, you can see how the number of objects changes. So for example, since the previous stop, there appeared like 3 more memory class objects, and 2 classes were probably loaded and created 1 more string, and so on and so forth. So you can step in your program and see how the memory changes, and you can even call the garbage collection from the evaluator and also see how the number of objects changes in the Java heap. From here, you can also track new instances of the objects. So if we say, ask it to track new instances from here, and we restart it, and we skip to the next breakpoint, you can see that now it has the link here. So if we click, you can see for every object that was created since our last stop, the creation stack. So this one, well, in this context, of course, it's not that interesting. But for some objects, sometimes it's really interesting to see where the constructors were called for them. And you can do that from the memory view. So let's untrack them. OK. Some nice settings of the debugger, which you may be interested to change when you at some pro level of debugger knowledge. So as I said before, it is really easy to delete a breakpoint if you simply click on that and it's gone. So you may be interested in changing that, and there's a special settings for this here in the debugger settings, which is called remove breakpoint. So by default, you click, and also you can drag or click with the middle mouse button. I usually use this just because I tend to delete breakpoints a lot and I don't want to restore them. So on the first click, I create a breakpoint. On the second click, I disable the breakpoint. So if I want to get back to that breakpoint, I enable it again, and so on. So no more deletion by click. And to delete it, I either click it with the middle mouse button or drag it to the editor. This is, for me, much useful. Also, we have the confirm removal of conditional or logging breakpoints. So if you don't want to be that radical and change the behavior, you can enable this. And if you have a breakpoint with a condition, oops, it will ask you every time you want to remove this breakpoint. I don't know, for some people it is useful, but I find this radical way of removing breakpoint more useful. Also, the default delay for the tooltips in the debugger is 700 milliseconds, which for me is too big, too long. So you can set it to something like 100 milliseconds, or maybe 0, but 0 is once again too radical. Also, if you're a keyboard lover and you don't want to use the quick evaluate shortcut, you can enable the show value tooltip on code selection. And this way, to evaluate something, you just need to select it. So you can just enlarge the selection like here. Oops, I use mouse, so I don't, yeah, like this. So for people really who really don't like mouse, this could be useful. And one last thing is the null elements in the collection and arrays. And by default, we don't show them. And even though we are showing a special hint for this, many people don't understand why there is no nulls there. So if you don't like this, if you don't like this behavior, you can go here to the data view settings and unselect this setting, and null objects will be there in the collection. For some people, this is more useful than not having them. So let's continue. The Hotswap. The JVM has the ability to change the bodies of the methods on the fly. And in the debugger, you can easily use this using the reload or the Hotswap functionality. So for example, we appeared in this nice method, which is printing the integer parameter plus 100. And for some reason, we would like it to print plus 1000, for example. So of course, we can stop it, we can recompile it, restart it, and then see what's happened. But there's an easier way. We change the code. We call a special action called compile and reload file, and it will recompile this one particular file and reload it in the debugger. And you will see that the current method is now obsolete with a nice red icon. And obsolete doesn't mean anything dangerous. It only means that the new version of the method will be in effect only on the next entry to the method, because JVM doesn't want anything to be broken. So in the process of execution of the method, it will not kind of replace the code. So when you exit the method and stop there on the next iteration, the new code will be in effect. So you can see that now it prints the plus 1000. Also, if you don't want to skip the current kind of call of the method, and you want it to be processed with the same parameter value, so let's change it to back to 100 and compile and reload again. And what if we want it to be executed with the I equals to 0? We can do a trick using the drop frame. So we drop this frame and we enter it again. And now the method will be executed with the same parameters and with the new bytecode changed. So we can step over and see that it produced the new result which we expect. This is the easy way to change the body of the method you are already in currently. And please don't try to change the main method on the fly, because you will not be able to see the difference, because you will not be able to drop the main frame and step into that again. So only on restart you will see the difference. What else can you do with the Hotswap? So other than changing the application on the fly, so you can check your fix of the bug right there without restarting the application. Also, there's another use case. So check this code. So it does a lot of iterations. And for example, you are interested in one of them with a special I equals to, I don't know, 100,000. So if you start this application, even though this condition is really simple, but the number of condition checks is so huge that you will probably not be able to wait until it triggers. So there's a way to work around this. So one of them is to hard code this condition right into the application. So you can easily do this here and then set a breakpoint here, and this would be usual breakpoint, and you can recompile, restart it, and then immediately stop right there where you want it to. So we have a +1000 here, so it's okay that it's a different number here. But you can do the same using the Hotswap. So for example, if you want to be stopped here, so let's delete it and restart the application, and for example, stop on the first iteration, but we want it to stop on the iteration number 100,000. So I haven't yet recompiled and reloaded the code, so you can see that the breakpoint is invalid. But when I compile and reload the file and it will be reloaded, the breakpoint will become checked. So now it will work. Yes. So let's skip this back. Yes. So this way you can work around the conditional breakpoints, which are really frequently used, and you are not able to wait until the condition is true. What else? In the debugger, so last time we discussed the remote connection of the debugger, but actually for the debugger, any connection is remote. So even processes on the local machine is attached the same way you attach the process on a different machine, so it's a socket. For local processes, you can attach to them using the attach to process action. Let's do this. And you can see that now it finds only one Java process, and it states that it can do read-only attach. So what is that? So if we haven't provided the VM option for the process, which we discussed before with that debug agent and so on, you can still attach the debugger using this read-only mode. And this mode is like this. You suspend the application altogether, and you can see the threads, you can see the frames, you can see the local variables and the content of the memory, but you cannot do the stepping. So you can suspend all the applications, see what's happening inside, and then resume everything at once. So no breakpoints, no evaluation, but you will be able to see what's happening at the moment. So let's try this. This launcher is the, on Mac, it requires this super user privileges. So this process is actually the compile server of this IDEA. So you can check the processes it has. You can see what's happening inside every process with every value of every variable. And you can also see the memory view for this. This is much more useful than the regular thread dumps because, well, thread dumps does not provide you with any information about variable values. And here you can see, you can check whatever you want. Like for every frame, you have the values. This is sometimes much more useful than regular thread dumps. But also you can use this for different things. So consider this simple application which runs the, oops, I already have, which runs the JDB. JDB is a command line debugger from the JDK. So I just use it as an example of the process which waits for the user input here. So we have this process right now running, and we can see that it is in the list of the Java processes in the system. Here it is. So we can do the read-only attach and observe what's happening inside. Let's type the password. So you can see that it starts from the main, and the main is actually CompSunTools example debug. So if you didn't know, the JDB is an example inside the JDK, is an example application of how you can write a command line tool for the APIs. Okay, so in read-only mode, it's not that interesting. So what if we want to debug it with the debug agent? So where do we provide this debug agent? So JDB does not accept the VM options from the command line because it has its own starter. JDB is an executable in the system. Well, actually, there is a way. There is a special environment variable called Java tool options. If the virtual machine, Java virtual machine is started and it sees that this variable is set, it adds the value to the VM option of the virtual machine. So how we can use this? We can provide this variable, and we can set the value of this variable to the debug agent line. So this is exactly the same line we used for remote debugging before, with one difference is that we don't specify the address because, well, if the address is like fixed number, it will be used for every virtual machine. And so second invocation of the virtual machine will have the same address and will not be able to start. So we don't provide it so that the virtual machine is able to auto detect any available address and use it. So now let's provide this environmental variable to the process, and let's run it instead of debug because this environmental variable interfere with the regular debugger from the IDEA. So we run it. It has detected the option. So this is from the JVM. It's not our output. The JVM on startup detected that this environmental variable is set, and it used it. And you can see that it assigned the port to this process. But also, if we go to the attached to process list, you will see that it assigned a port to the JDB process as well. So this is this one, and this is the JDB process from the sub process which started from here. So now we can attach it using the regular debugger attach, not the read-only. So what do we do here? So we can pause it and we can see, well, almost the same picture we had in the read-only attach. So how do we proceed with this? So let's add a breakpoint here, for example. So after the read line is completed, we will be able to stop here. But how do we provide input to the process, which we started from another process, and we actually don't assign, we haven't assigned anyhow streams. So let's attach to this process as well. So now we attach to this process, and let's stop on the breakpoint here. Let's get the process stream. And let's write something there, like hello. And I know that we also need to flush the stream. Voila. You can see that the hello is now available on the breakpoint in that another process, and we can step-by-step debug that and see what's happening inside the another process. Even though we haven't anyhow affected the startup line, using this environmental variable, we are able to debug it now. So sometimes it is useful. So using this technique, you don't have to rely on some debug options for the sub-processes inside another kind of process. You can use it to debug like anything, anywhere. Okay. What else? Also, I forgot to tell you that if you have a running process already and you have a tool window for that, there's a special button here called Attach Debugger, so you don't have to go to the Attach to Process list. You can attach the debugger to this exact process right from the tool window. And also for read-only attach, this is also available. So instead of doing a thread dump from the tool window, you can attach a read-only debugger and have much more information. Debug decompiled code. What if you want to debug an application and you don't have source code for that application at all? Consider this example. I have a toolbox here, and I have installed the release version of the IDEA Ultimate 19.3.3. So I can go to the settings, if you can see that. I can go to the VM options and add the line for the debugger agent. Then I can start this IDEA. And go to the attach to process. You can see this IDEA in the list, and I can attach. So now I can debug this application, but I don't have sources for this. And one way to find the sources is to, well, get to the GitHub and fetch them. And for IDEA repository, it takes like some time, quite some time. And another way I will show you right now. So you can pause here, and you can see some frames from JDK and some frames from the IntelliJ IDEA, but there's no sources. There are no sources. So if you click, you can see the local variables, but no source. There is a way to work around this. So if you go to the project settings, and before that, let's go to the toolbox and copy the install location. Now let's, and this project which we are currently in, it has nothing inside. So it's an empty module, just some dependencies for the demo, like JetBrains annotations and so on, but no source code for the IDEA, of course. So, and this is also the annotations artifact. So let's add a Java library to the project. And from here, I know the extra strange mark shortcut to go directly to the path I copied from there. It's a secret. So from here, let's add the whole lib folder of the installed IDEA. And we will add it as a dependency, and it will take some time to index this. But after that, if you click on the IntelliJ source or the frame from the IntelliJ sources, you will see that now we have something. And it looks like the source code. Well, basically, it is the source code, but it's not the real source code. It is the decompiled class file, as it states here on the top. So what it does is it takes the class file from the jar, from that lib folder we have provided, and it decompiles that because the IDEA has the decompiler built in. and it provides you with the decompiled source code. But the debugger is fully integrated with the decompiler. So now you can step by step go through the code. You can do this step into step over everything else. So sometimes the decompilation process is not that absolutely correct, but the code will look almost as the real source code for the application. So we don't have the source code, but we can debug it, and we can see the local variables. And also, of course, because it is a real debugger, we can do things like this. So let's, oops, we have a lot of breakpoints. So let's open something in this IDEA. And I know that there's a nice class inside the IDEA, which is the editor impl, my favorite. Let's go there. And once again, it is decompiled. So we have the paint method, which is the main method doing the painting inside the IDEA code. So let's get back. And now immediately we have it painted, and we have stopped on the breakpoint. So let's see what we have here in the editor, a lot of fields. And I am interested in the background field. So we have this nice field here. Let's change it to something like color green. Oops. And let's resume it. Yeah, you can see we didn't have sources for this IDEA, but we were able to debug it, stop somewhere in a real position, and change the value. So this way, actually, even without sources, you can debug almost any application. The things you need for this is the bytecode. So you need to have the access to the class files. And there may be some tricks to make it harder, like stripping of the debug symbols from the class files, or the obfuscation of the bytecode. But in many situations, this approach works really nice. So let's get back. And please don't use this for illegal things. When you first use the decompiler, there's a special kind of agreement that you're stepping to the really dark territory. So we are not responsible for anything you are doing with this super technology. OK. Async stack traces. So in modern world, with many threads and cores, and when people are really interested in making their hardware working really hardworking, sometimes it's really hard to debug the code written in the async way. So consider this example. We have the get line, which is called inside the run async completable future, which what it does, it basically calls this get line on a separate thread and then waits for the result. So if we debug this, and I will disable async stack traces for now. If you debug it in any other debugger, not the IntelliJ, you will see the picture like this. So the stack trace of this getLine invocation does not contain anything even close to the main method. So it is the insights of the executor, which is used for the completable future run async. And if you stop somewhere inside the getLine method, you will not be able to find out where you came from. So where this getLine was kind of scheduled for execution. And here we do that again. So inside this async kind of processing, we do this again. So if you stop here, you don't know anything about the getLine method. And of course, you don't know anything about the main method, which was kind of the root cause of all this processing, but not in IDEA. So I enable back the async stack traces, and they are enabled by default. So if we filter out the uninteresting stuff, you can see that now you can see the logical async stack trace. So first frame is the kind of second schedule, and the last frame here is the main thread or main method. So this way, it is really easy to see how the work chunks are processed and where they are scheduled and where the kind of real processing is happening. There are some limitations to this. So for example, in the so-called captured stack frames or stack traces here, you will not be able to see the local variables, but that's the limitation. It takes too much time to record that information as well. So by default, this technology is kind of used for most common executors from the JDK. Invocator from Swing and some other things. Also, if you have your own executors in your application, there's a way to make async stack traces available for you as well. So this is a really simple example of the custom scheduler or the executor. So we have a queue, and we have a thread which process the elements in the queue. And we have a schedule method which kind of adds the element to the queue, and we have the process method which kind of doing the processing. So without the async stack traces, if you stop inside the process method, you will see the stack, well, almost like we had before. So nothing that looks like the schedule method. Well, we are interested in the information about where the schedule method was called for this piece of work. So we have a special annotation in the JetBrains annotations package, especially for this. And the annotation is called the async schedule and the async execute. And the schedule is for the place where you schedule the work. So you mark the key, which will be used for matching the execute part later. And then the execute annotation is used in the process method. So you set the annotations like this, and you don't need anything else in your application. Let's restart it. And now you can see that inside the stack trace, you can see the async stack trace, and it shows you the exact schedule position. So for the first process invocation, it is the first schedule. For the second, it is the second. And for the third, it is the third. So in the IDEA project, we have annotated several, we have already annotated several custom schedulers we have in the code, like later invocator or alarm and some other. So if you have more examples, please annotate them or contact me, and I will help you doing this. Stream debugger. We have already checked some examples of the streams and saw how complicated it may be to debug them. But there is a solution, a nice solution, which is called Stream Debugger. So if you have a stream and it's really hard to understand what's happening inside, so it calls some factorize method and other stream operations after that. And also the input is rather complicated. There's a special action for analyzing what's happening inside, which is called the trace stream chain. And you click on that. it will evaluate the stream and provide you with the image of the transitions which is happening inside the stream. So you can see that every, oh my God, let's disable that render. It is so strange. Yes. So every input in the stream, you can see how it is processed in the stream processing. So, for example, this flat map obviously calls that factorize. So for every input, you can have more than one output, and then the distinct will remove duplicates, and you can see how it's happening visually. And then it sorts that, and then to array basically puts everything to array. So it is very easy to see visually what's happening inside the stream. And it's not necessarily have to be integers here. You can have any type of objects. Also, the flat mode produce this nice picture of what's happening from the beginning to the end. And if you click anywhere, it will show you the path of the element through the stream processing. Sometimes it's really easier to understand what's happening here than doing the real debug. What if you have a breakpoint, and as we have seen before, you may have a breakpoint with a condition, doing some hard work, checking something, but as you can see here, nothing is happening. So the application is doing something, but we don't know what. So for us, it looks like the application hanged or something like that. But the problem is that we forgot the breakpoint with the condition. So how do we figure this out? So in this case, it's obvious, but in an application with a huge code base, it may not be that obvious. So there's a special view for this called the overhead view. And it records and shows you the overhead of different elements in the object, different processes happening inside the debugger. So now you can see that the breakpoint was never hit, but it takes a lot of time for processing. And you can disable it right from here. So let's set a breakpoint somewhere else, if we can. No, yes. And we can disable it, and this way we can quickly find some breakpoints, possibly with conditions, which slows down your application. And if you don't need them, you can disable them from there at once. And also it shows some more nice things there. So it shows you the renderers. So this is the array renderer. And if you step, you can see that it takes sometimes, well, not much, but some renderers may take a lot of time to evaluate. So if you see that your stepping is slow and some of your renderers consume a lot of time, you can disable these renderers and step a little bit faster. And also you can see that show method return values is here. Though we don't show the exact time it took, but on every step it takes some time to provide you with the last return value of the last method. Also, I don't think I was talking about this feature, or maybe yes, but it shows you the last return value of the method. So if you don't have it somewhere, anywhere recorded, sometimes it's really useful to have it here. But it consumes some cycles, so if you don't need it, please disable it to be able to do the stepping faster. So this view is the first place to go if you see that the application in the debugger is working slower than it is expected. First, open the overhead view. Maybe you have forgotten something and it consumes the CPU. Some things to say about watches. So usually a watch is an expression which will be evaluated in every context. So if you have something specific there, in most contexts, you will have the unable to evaluate everywhere. So for example, if we add this kind of A here, so strange case, but anyway, if we go to another thread, of course, there will be no such variable here as A. So for some cases, there is a solution called class level watches. If you're interested in a specific expression for a specific type only, so for example, we have a string here, and maybe for a string, we are interested in having the length available inside. So you can add a class level watch to this type of object. So in this case, it's string. And you will be able to see this for every string object. And let's add something else. So for example, we would like to see if it starts with A. And you can see it's true. So let's go to the memory view and see what we have for other strings. So you can see that we have these class level watches here because we added them for the string object. And you can quickly see the values for any string objects now. Also, if you're interested in a particular field, so if you have a lot of fields in the class, you may be interested in some of them first. So you can add them as a class level watch, but there's an easier solution. You can click on this flag or call the pin to top action. And it will just move this field to the top of the list. Also, class level watches are implemented using the renderers. So if you go here, well, in presentation mode, you cannot see this. Let me show you like this. If you go to the settings, you can see that these expressions are added to the list of the fields, and you can make them on demand. So if, for example, this expression is kind of may take long to evaluate, and you don't want it to be evaluated for every string, you can make it on demand, and it will be evaluated only when you click here. So for example, you can add some hardcore processing there, make it on demand, and evaluate it only when you need it for this particular method. Also, you can unpin, of course, if you don't need that. So let's see if it works for any, yes, it works for any method or any string object now. And of course, this is not only for strings. You can use it for any type of objects. Another question which people usually ask is when you suspend your application using the suspend button or pause, you cannot evaluate. So you can see this message here that the VM is not paused by the breakpoint request, so you cannot evaluate. So even if you want to get something as easy as system get properties, you cannot do that because it's a limitation of the JVM. So what can you do in this case? Well, the solution is actually easy. You can do a step. And usually in many situations after the suspend, you can do the step. So if it's not the endless wait in this thread, if it does some like processing like event dispatch thread or something like that, you will be able to do a step. And then in this context, you can easily do the evaluation. So this way you can work around this limitation of the JVM in many, many cases, if not all. Actually, this is it. Now you can debug much better, maybe like a professional. Thank you. And your questions. Any questions? There's a microphone right there. Munich? Oh my God, 2 people there. Any questions? No. Alexei, have a question. Give him the microphone.
When you debug compiled sources without any sources, really, can your debugger download class files?
Can your debugger download class files? Download from where? Or you mean the source code?
Debugs something, it knows where to download from.
It can download, it could possibly download this for a community version, but probably not for the ultimate. Microphone doesn't work, it seems.
Hello. Oh.
Now it works.
Why
so the
can't
question was,
why,
I can repeat it. The question was, why can't the debugger download the source code or the classes for the application being debugged? Yes?
Yes.
And my answer was that it probably can do that for the, you mean automatically add it to as a library or what?
You can do step, you can do show frame.
I understand. So get it from the debugger, like the bytecode.
Yes, and if debugger can do all these things, can't it should know the
yes, it knows.
The bytecode.
Yes, it knows. So the debugger can get the bytecode from the application itself. It's true. It can get the bytecode of the method. So there is a request to do that even without the operations I showed you with the lib folder and so on. So it is technically possible to do this, yes. But it is not yet done because there are some limitations to the bytecode provided by the debugger. So for example, it does not provide you with the exceptions table. So decompilation of this is tricky. So we don't do that now, but maybe we'll do that in future. No questions.
Thank you.
That's it then. Thank you. Is there a question, Munich? No. Okay. Thank you. Bye-bye.